You're probably watching this video somewhere on Earth. A planet going around the sun, a star spinning around the center of the Milky Way, a galaxy and a swarm with 50 others, all dancing with 100 other galaxy groups in our supercluster. And well, that's as big as it gets. If we keep zooming out, superclusters don't form super-duper clusters. They're connected by thin filaments, a tangled web forming the biggest structures in the universe, threads of superclusters separated by millions of light years worth of nothing. But why? Why not some other structure, like one giant mega galaxy sprinkled with stars? In fact, why does the universe have any structure at all? First, imagine a different universe from our own, where all the matter is spread out perfectly smooth and uniform. Just like our universe, every piece of matter is attracted to every other piece thanks to gravity. If that universe is finite, if it has an edge where matter ends, then everything would be pulled to the center and end up in one clump. Lucky for us, this isn't the universe we live in. But what if this smooth and uniform universe had no edge, spreading out forever? A particle inside this infinite cloud would feel nothing, or rather, it'd feel gravity equally in all directions. The whole universe would be frozen in place. But our universe isn't evenly spread out, and it isn't clumped in one spot. It's full of structures at massively different scales. To find out how our universe ended up this way, let's run the clock backwards. When scientists simulate the evolving universe, they find out that in order to make one that looks like ours, there needs to be some tiny lumps in the very beginning, in order to seed the structures we see today. What makes these early microscopic lumps? Because the universe is expanding today, we know it was denser in the past. Go back in time far enough, and it was filled with a super thick plasma, like the inside of a star. But at the smallest scales, the uncertainty of quantum mechanics sprinkled some randomness among those particles, forming tiny quantum lumps instead of a smooth matter batter. Then the universe expanded so fast that lumps the size of a few atoms would have been stretched out over a light year in a fraction of a second, locking these tiny quantum fluctuations into place all over the universe. This is called inflation. The biggest things in our universe form thanks to the smallest. How do we know what happened in those billionths of a second following the Big Bang? Well, it turns out we have a baby picture. The cosmic microwave background, some of the oldest light in the universe, shows these early fluctuations as they looked just 400,000 years later. Some spots are slightly warmer, some are slightly colder. The size and magnitude of these lumps exactly match what cosmic inflation predicts. With some help from the dark matter around it, those stretched out lumps of stuff coalesced, forming planets, stars, and galaxies. But after inflation, thanks to dark energy, the universe kept expanding. On one side, dark energy's pulling everything apart, while on the other, gravity's scrambling to pull things together. But gravity can only pull so much. At the largest scales, dark energy wins, and things get separated. If the universe had more dark energy, things would be more spread out. And in a universe with less dark energy, the cosmic web would be woven tighter. Depending on the unknown future of dark energy, in a few billion years, gravity might form super-duper clusters. Or dark energy might rip everything apart. We live in a universe shaped by the tug-of-war between gravity and expansion. The unfathomable hugeness of galaxies and clusters and filaments were set on course by the tiniest subatomic flickers. We may not have super-duper clusters, but this story is still super-duper on its own. Stay curious. Hey guys, this episode was a collaboration with my friend Jorge Cham, who makes the awesome PhD comics, and physicist Daniel Whiteson. They have a new book out called We Have No Idea. This video is based on a chapter called How Big is the Universe? And Why is it so empty? This is a really fun look at what we know about our universe and a lot about what we still don't know.